We first of all have to look at the grounds, the foundations, or the um, whatever we're going to build up off is what we need to look at first. So what we've got with a cold bridge or thermal bridge is the fact that the ground um, is going to suck any energy and out of the build. So we have to insulate that. We have to think about it and design something to prevent this from happening. This is a couple of examples because if you have a standard foundation with a concrete directly onto the ground, regardless of what you got underneath it, it's going to form some form of a cold bridge, potentially for the older houses, especially in the 60s and 70s, where we had a completely concrete floor, raft, if you like. It was one complete cold bridge. We have to allow for this for our foundations and how it works. So what we've got here is we actually have an insulated base, which is on a stone or a prepared level base underneath. And then a reinforced concrete ring beam with a concrete screed. Now, this is great because concrete is actually a thermal mass. It will actually absorb, store, and release energy almost on demand. So what we've done here is we've gone from a cold bridge, concrete being a cold bridge, to concrete being thermal mass because that's an insulated thermal floating raft, and we're building off that. So we've compensated for the ground already by design. And we can come off this either with a traditional build or a timber frame, and we can treat this insulated base the same as we would any traditional foundation. When it comes to connection points, now again with the new build, a connection point on a roof, joist, floors, wherever it may be, can be compensated easily by design. When it comes to a retrofit, it's a very different matter because what we have with a retrofit is we have a box, an existing box, with every joist, floor, roof connection being a cold bridge. We can't prevent that. What we can do is come up with a design, a way of overcoming and compensating for it. As you can see with these type of things here, you can see where or cold spots would be on these connection points. And we need to look at how we're going to compensate for that. Other connection points. As you can see, this is actually a new build, but it's with an insulated panel. The insulated panel has solid connection points in the corners and joints. So when we thermal image it, you can see the differences. Every connection point has a cold spot, a thermal bridge. This is where the energy or the heat is being drawn out of the building because it's got a direct connection. It does not have what we call a thermal break in between the outside and the inside. So therefore, the thermal bridge is crossing directly across to the outside and being drawn out that energy. Windows. Energy efficient windows are the way to go with any passive house or retrofit. Purposely designed windows could really make a difference to the house. Initially, they need to be airtight, so they need to be really sealed. So when the casement's closed, you've got an airtight seal. We have triple glazing, which is really good U values for triple glazing windows. Also now we have vacuum glazing as well, which is a lot thinner and lighter because there's less glass involved. But the windows really need to be thought about when it comes to thermal bridge because any mass is potentially a thermal bridge. Windows, thermal bridging on windows. These points here, this is where you get your thermal bridge on your frame, which is why you keep your frame to a minimum. So we have a box here and here with spaces in between. All these spaces and this mass here is full of insulation. That is to try and stop that cold bridge at that point. Penetrations and services. Okay, when we do a new build, we have to bring in services to the ground. We have to bring in soil pipes. We have to bring in water, electric, and whatever else may be required for that particular build. So what we try and do is we try and use insulated ducting. These are just a couple of points here of the ducting used for the MVHR system, the mechanical ventilated heat recovery system. Anything that goes from that to the outside needs to be insulated in some way. Nowadays, you can really get some good insulated pipes, including service pipes for 100 mil soil vent pipes, you name it. If you look for it and you research it, you can find them. These are really good for new builds. When it comes to retrofit, these penetrations are already there. So again, we have to look at the design and take into consideration how we're going to compensate for that. This is another one of the difficulties in retrofit, but these things can be solved by thinking about it and coming up with the solution. Every connection point and cold bridge can be dealt with, just got to be thought about individually and a little bit more on a retrofit. Pipe insulation, again, this is a pipe that would come into your ground. This would be a soil vent pipe or something similar to that. It's insulated. All you do is trim that back inside of the house for your connection points. Thermal breaks. What is a thermal break? Right, we've spoken about thermal bridge and how that is a bridge to lose your energy, and how you've got a piece of steel or timber or plastic or anything that goes from the inside of the build to the outside is going to be a thermal bridge and has to be compensated for. Steel is a big one. Many buildings now, especially in timber frames, still have to have some form of steel running through it for structural support. So we have to put in what we call a thermal break. What do we do with a thermal break? It is exactly self-explanatory, really, as a thermal bridge. Here, we have steel. What we've got in the middle here is we have a thermal break. So what that's doing is that's preventing energy from being sucked through from the outside. And this is an example of what a thermal bridge is. All this heat is being drawn from the outside. You can see how cold it is on the outside because all the blue. Anything red, orange and yellow is heat, is energy. All this is actually being drawn out of the house because it's a continuation, a continuous concrete or product through the build from the inside to the outside. So it could be 0 degrees out there and 20 degrees inside, but that 20 degrees inside is being reduced by the thermal bridge, exactly pulling that out of the building. That energy inside the build has to be replaced because you still wanted 20 degrees inside your house. So as the energy is being lost, we're reheating the house. And therefore, you are using so much more energy to heat the same space simply because the cold bridge hasn't been insulated for by a thermal break. So here we have some really clear examples of thermal breaks, or what we can do to help compensate for the steel, the windows, or whatever else is we got. When it comes to retrofit, often with a retrofit, they actually put steel in because you take walls out, you're redesigning the internal of the build. Regardless of whether you're doing an external insulation on a retrofit or an internal, there's still got to be thermal breaks that are thought about. Usually with a retrofit, the thermal break is the external insulation because you're compensating for that thermal bridge by putting the insulation on the outside. That is by design because it's just part of the process. You're naturally cancelling out any thermal bridges. The thing is, though, with internal insulation on your retrofit, this is where it gets a little bit more difficult. It's simply because we have to look at each individual connection point and decide how we're going to compensate for that energy loss. Steel, what we'd have is a thermal brake plate. That thermal brake plate there's a number of different materials out there now. I'm not going to name one in particular, but there are a number of structural insulators now that you can use for these thermal brakes. Around windows, your thermal brake is your insulation. You've got insulation within the frame. You've got insulation around the outside of the frame and even connected